All right, let's get rolling here. So what we have here is, like it says, there's a light source actually, to be more explicit, and then a detector. And so this is easy. You could put a flashlight, set it on a little stand, aim it at a light detector, and you would, or at a mirror, and have it bounce back off. Okay, that's the way we measure the speed of light, as a two-way trip. We know the distance involved, etc., etc. So that's the experiment. All right, and that's a simple experiment. We could do that sort of thing just about anywhere, and speed of light's been measured pretty accurately by that method, and more accurately by the vibration of various radioactive elements. And so what we're going to do now, though, is we're going to put this experiment into a situation where one observer sees one thing and another observer far away sees something else. And so this is going to be in the frame of reference of, say, an astronaut on space station. All right? So that space station is in orbit. All right? It's moving. And so if it were possible, Superman supervision, looking through the wall of the space station where this regular old astronaut standing there doing their little light experiment, where they shoot a beam of light along some distance that we'll give a name to short enough, and then bounces back. So in the astronaut's frame of reference, they can't actually see the beam of light make the trip. They just see the beam of light, and they get this detection. But down on Earth, so hundreds of miles away perhaps, this special observer is watching that same experiment, except that observer doesn't see the light go along a straight line. In fact, the observer sees two things. The observer, okay, so if we put our same mirror over here, the observer on Earth sees the light source shoot a beam to the mirror, and then it bounces off that mirror and hits the detector. And the reason for that is because the ship has gone some distance. Okay? The space station has moved. So the space station's moving, okay? And then this light beam is shot at a mirror, okay, which moves. So I'm exaggerating the distance for the sake of the mathematical analysis. So there's a couple of spots in here where it's tough to imagine. And this first step is the first one. The only hard parts after this are some of the algebraic maneuvers, okay? But from the observer's point of view on Earth, hundreds of miles away, the whole thing's moving. And so this beam doesn't just take a straight back and forth thing like the astronaut imagines or is looking at this tabletop experiment, if you will, okay? This observer is watching the whole thing move. So that mirror moves. Okay, so here they're together. If you imagine, put your hands, stack them on, and your bottom hand is the light source and the top hand is the mirror. And this is moving, and so you have to trace out this triangle bit for the motion. So what we're going to do is try to combine the two frames of reference. So, well, I'm going to do that in a different viewpoint. So this is earthbound observer. Okay? And so let's be clear about what each one sees, or take a swing at that. So the astronaut sees the light beam travel, and we'll call the distance D. I haven't labeled it yet. A distance D in a time that we'll call, I don't think I have a delta symbol. No. What in the world was that? Here we go. We'll just say delta T, and I'm going to say T naught, but that's not initial. Okay, so we'll explain that here in a minute. But the earthbound observer sees the beam of light travel what I'm going to call two lengths of S. That's what those red lines are going to be on that side of the thing. While the station moves 2L, which is going to be the length of that green line, okay, in just regular delta T. All right, so let's come in here, and so this distance, we'll call this distance D. All right, each one of these is a length L, and each one of these is a length S, just for, we could pick any letters we want. So this is the geometry of the situation, which is going to lead us to some trigonometry. So again, from the astronaut's point of view, their tabletop experiment, so to speak, or in their room on the space station, is shoot a beam of light straight across the room. It bounces off a mirror, comes back to the detector right next to the source. So their offset is so small that the only person who could detect the offset of those two things would be the observer there. The person on Earth couldn't tell that there was any, that the detector was right next to the source, an inch away or something like that. But there could have been even a foot away. It really wouldn't matter. Okay? Essentially a straight line. Down on Earth, however, the super person with supervision looking through the wall, unless we have glass walls on the space station, which I'm pretty sure we don't, they see the whole dang thing moving. The astronaut doesn't feel like the light source isn't moving as far as the astronaut's concerned, because the astronaut and the space station have the same speed. As far as the astronaut's concerned, nothing inside the space station moved. But the observer on Earth sees two things. Sees the whole space station move, which necessarily means the light beam takes this bouncy, angled path instead of a straight back and forth path. All right, so here, these are frames of reference. All right, so let me kind of redraw the situation again, just a little bit bigger. So the light beam from the Earth-bound observer's point of view travels S, so this is light source, light detector, the mirror that it bounces off, but the astronaut just sees a back and forth along some distance d, and we'll call each one of these lengths L. So this is a combined frames of reference. Frame of reference of the astronaut in blue, frame of reference of the Earth-bound observer in the other two colors. All right? So let's think about this. So the Earth-bound frame of reference has a distance of 2s, okay? And the light beam is going the speed of light, which is called c, and some delta t. So that's just distance equals rate times time, or the first zeroth law. That's really first zeroth law application of what the Earth-bound observer sees. All right? And the Earth-bound observer also sees the distance 2L, the total distance that this bouncy beam traveled according to that observer, and the speed of the ship, which is obviously less than the speed of light, much, much less than the speed of light, also in that same delta t. But as far as the astronaut's concerned, light beam went double that distance across the room, back and forth, at the speed of light, and then we use this delta t naught. So let's be clear here. Delta t naught. Okay, what in the world does that mean? Delta t naught is what we call proper time. And proper time is the frame of reference where it happens. Frame of reference where an observer sees the event. Okay? That's what we mean by proper time. That's a piece of jargon that you only hear about in relativistic thinking. Special relativity. Yeah.
What does the C represent?
Speed of light.
Okay.
C is our speed of light is what we use the letter C for it. Okay? And in the movie that we're about to watch, that will be explained. It's a Latin thing, and there we go. So here's some pretty basic math and basic kinematics that explain this interesting disconnect between what one observer sees about the motion of something versus what another observer sees. Okay? We could do the same sort of thing. Somebody could sit on the side of a lake and watch a raft cross the lake on the other side and watch a swimmer swim at angles like you see in red here. And from that viewpoint, you would see speeds in one sense, but the observer, the swimmer, would have a different viewpoint, as would the rafter. And so the cool thing about relativity is that it all sorts out, and we understand that the speeds are what they actually are in the observer's frame of reference, in spite of them being different in someone else's frame of reference. And that's the thing about special relativity. Einstein really pulled a novel rabbit out of the hat, so to speak. All right, so what we're going to do now, you have that triangle before, and what we can say right off the bat with that triangle is L squared plus D squared equals S squared. That literally relates the two different things that the earthbound observer sees with the thing that the other frame of reference sees. So the Pythagorean theorem on the situation that lends itself to a right triangle lets us put two frames of reference into one mathematical statement, okay? Because what we need to do, okay, we need a way to relate proper time to another frame of reference. That's what we need. And so that equation lets us get away with it. So let's see what we get if we plug and chug those things into it. So each one of those equations has S, L, and D, or should have worked it out to be LSD, but oh well, that would be bad. All right. So L will be, if you just solve that 2L equation for L, you'll get V delta T over 2. It gets squared. The D squared equation will be C delta T naught. It's got that special proper time bit going for it. And then S squared is dealing with the speed of light, and that'll be C delta T over 2 squared. Okay? Door giving trouble. And of course, since everything is over a 2 squared, we could just drop that denominator, okay? And now it's kind of flat, and this is intermediate algebra. This is not difficult stuff. And so what I want, if I want a way to relate, we need a way to relate it. I gotta well, end up deleting that. Need to relate, which means I need a relation. I just have to rewrite with that to other frame. So if I need to relate them, then I need to have this change in time equals some mathematical mishmash of this other time. All right? So that's what we're going to do. We're going to get the common things, namely time, since that's our interest here. And so a little rearranging. C delta t squared minus V delta t squared will equal the C delta t naught squared. And again, the t naught is not t initial. And sometimes they'll use the letter tau like we use for torque. Different books like to pitch it different ways, or t prime, which I think is worse. But we have to do something. There's still time and all that. So now the thing that can happen is I can pull a delta t squared out of this business, and that leaves me with a c squared minus v squared, and I can pull the c out there, and I get delta, or c squared rather. So now it's starting to shape up, okay, in a way that we can actually relate, make sure I put the knot there, relate regular time to this proper time business. Because in proper time, it happened just like you would expect it to happen. It was that other frame of reference where it looks different. It took a longer path than the other observer saw. That can't be right. You know, only one thing happened. Okay? And that's the weird thing about things that are going the speed of light, is we have this relativistic effect that if we don't account for it, well, then you don't get things like GPS working. GPS works because of this, special relativity and general relativity. So those satellites that are doing all that stuff, back and forth, all of this stuff has to go underneath the hood mathematically for your GPS to work. All right, so I'm going to go to a new screen since I'm running out of space on this one. So what happens is we get to delta t squared is going to equal c squared over c squared minus v squared times this proper time squared. And you're thinking, okay, I could just take the square root and things would work out all fine and dandy. But what we're going to do first is try to simplify things a little bit here. I can divide numerator and denominator by the same thing. That's the same as multiplying by a fancy form of 1, really. Okay? And so I'll get my delta t squared, but now it'll be 1 over 1 minus v squared over c squared, which is a little better, times this delta t naught squared. So if you take the square root, okay, all this business, you'll get delta t equals the square root of 1 over this 1 minus an interesting ratio times the proper time. And what we end up doing is we call this thing gamma. So delta t will equal this gamma delta t naught. All right, so we create this new letter because it's easier to deal with it. And so this is called the Lorentz factor, some fellow named Lorentz, okay? And basically it converts one time into another time. It converts proper time, the way an observer at the location where the event happened, okay, into another frame of reference based on relative speeds, speed of an object relative to the speed of light. Now, this is called time dilation. So if you were to look this up in your textbook in chapter 29 or 8 or 30, something like that, I forget where it's at. It's usually late in the textbooks. It could be earlier, but it tends to not be. And the reason it tends to not be is this factor applies to not just time. This is called time contraction, because the way we put it, but length contraction, because when things start going fast, it appears like they shrink and stretch. So if you've seen like Star Trek and other things, when things try to jump to light speed, you see this stretching out of things. All right. We also see light shifted, red shifting of, say, galaxies, their spectra and whatnot. And so a galaxy that's 10 billion light years away will seem to be, it'll be red shifted in a way. If it's receding from us, it'll be red shifted. If it's moving towards us, which not many are, it'll be blue shifted, the wavelength of light. So these relativistic things apply to everything: momentum, energy, time, distance, which makes sense. If this applies to time, then it's going to apply to distance. And guess what we built momentum and energy from? The first and second zeroth laws when we think of inertia. So this applies to energy, et cetera, et cetera. So, but that's the thing. So we would get, if we continued and redid it for another example, we would get a change, a change in distance, or length rather. Actually, let me be careful. We would find that length would be gamma initial length. So something's starting to head towards a noticeable fraction of the speed of light, then it will appear to stretch, either longer or shorter depending on the direction it's going. All right, so I showed the time contraction. The length contraction would be the same basic set of maneuvers yielding the same result. So I don't, if you want to look that up and just for the fun of it, you could just go check your textbook. So there's that.